All right, let's begin. So we would ultimately have finished this material last week, but like we said, the internet didn't want to cooperate with us. So we're going to finish up the Newton-Raphson and specific applications to power systems. How come it didn't start on that page? Sorry, this is like blocking my flow here. So what we left off with was if we knew all the bus voltages, we wouldn't need to do a load flow. We could calculate currents and get power flows throughout the system. But generally speaking, we don't know what the bus voltages are, so we need to have a way of calculating them. Because knowing the bus voltages, both magnitudes and angles, and having a system model, which means having Y bus, we would be able to calculate all the power flows. So we can't use the Y bus, the V equals Y bus inverse times I, to solve for that. We have to figure out a way of writing equations to actually allow us to solve for the voltages. And since the systems are nonlinear in nature, we have sines and cosines, right? We have complex numbers there. We have to use the Newton-Raphson, or we do use the Newton-Raphson algorithm to go ahead and solve that. But what do we need to solve? We have two things we don't know. First off, we don't know what variables we're trying to solve for. And secondly, we don't know what equations to use to help us solve for the actual values. So we have two things to do. We have to figure out what state variables we're solving for. Those are the unknown bus voltages. And then we have to use our power balance equations. Those are the f of x, the root finding ones that we have. And that's why they're called power balance and not power injection, because the power injected at a specific bus should equal the scheduled power at that bus. So that way you've got the right bus voltages. So let's start off by applying KCL at all of the buses. And we know that our injected current, so current coming into the bus from other lines, has to be equal to the generated power minus the demand power. So what I mean by that is if I have a bus and I have a generator connected to it, that's not going to get represented properly with Y bus, right? That's an external part of it. So it's not going to be necessarily included in there. Similarly, the demanded power, that's the actual power to the load. So those are going to be fixed power values, right? Fixed P and possibly fixed Q. So we know what those are, and we can write our current injection equation just to be equal to the difference of the two. Now, again, the current injected in there could be positive or negative, right? Just like with KCL, when we assume a direction of current, our injected current doesn't have to be necessarily positive going into a bus. It could be negative in that the current and the power is flowing out of the bus. Then we can go ahead and we can rewrite our equation as a bunch of the voltage differences multiplied by our Y bus. We did that already at the beginning of the semester. So we can figure out all of the injected current is going to be determined by whatever line is connected to that bus by taking the difference in voltage between those two buses and essentially multiplying by the impedance that's there. So then we can go ahead and get the actual power injected at any specific bus location is S equals VI conjugate. We know that equation pretty well. So we're going to substitute in our Y bus equation. And we do that because we're trying to solve for bus voltages, the V's. We're not trying to solve for current, at least initially. We will eventually. But once we have those bus voltages, we can solve for the current. So if you look at this equation over here, it's all based on voltages and Y bus. You're solving for the the bus voltages, and you've calculated the Y bus initially. So if you can use your nonlinear equations to solve for the voltages, you have all the equations and all unknowns that you have. Now, here's the hard part about Newton-Raphson. Do you remember how we tried to solve Newton-Raphson with complex numbers and it kind of burped at us? It didn't work that way. Remember we tried to solve for the square root of negative 1 or J, I should say the square root of -1 or J1? It didn't work. So the same thing here, we have to take our Newton-Raphson equations, our power balance equations, and we have to convert those to purely real numbers. And how do we do that? We just start breaking up the bus voltages and the terms of the admittance matrix into their real and reactive parts, or their magnitude and angle parts. So we're going to define our YIK, that's the Y bus element between bus I and bus K, and we leave it generic because there's all kinds of buses, is GIK plus JBIK. G is the conductance of the connection between the two buses, and B is the susceptance of the two connections. Notice BIK is a scalar number. It is not, where's my pen? There it is. It is not complex. The complex J term has been pulled out in advance. So G and B are real numbers. Y is a complex number, but G and B are not. The same thing with our magnitudes of our voltages and angles. So we have VI, which is just a magnitude and an angle, but we're going to break that VI into its magnitude and angle. So even though voltage is a complex number, when I look at the magnitudes and the angles independently, there's no complex number associated. It's just part of the housekeeping to make sure that we have the angles there. And then the last thing on this slide is we have to define what theta IK is. It's just the subtraction between the two bus voltage angles. So it's theta I minus theta K. So now I'm going to go ahead and break up my power into real parts and imaginary parts. But I'm going to start off again with my equation, my total power equation, P plus JQ is equal to S equals VI conjugate. And I'm going to go ahead now and substitute and break up the complex numbers so that I have just real numbers. And you can see I've got magnitude V, magnitude I, VK, e to the j theta, the difference in there. And then I multiply that by the conductance and the susceptance of the line. Now, I'm going to get rid of the e to the j theta, because again, Newton-Raphson algorithm can't handle that. And I'm going to substitute Euler's identity, the cosine plus j sine, in for e to the j theta k. So my middle of the page or middle of the presentation expression is the total power, but sort of trying to break things up into real and reactive parts. So now all I need to do is that last equation before I define P and Q, I just figure out what is complex and what is real. So anytime there's a J, like when I multiply J sine theta K times GIK, that gets put into the Q. So you can see here, sine theta K, GIK, that's a complex number. So it's because of the J term, but the power, the reactive power Q, it's just G sine theta. Same thing over here. When I multiply these two, right, I end up with this term. When I multiply these two, that's purely real. So that's going to be part of the real power. That ends up over here. And when I multiply these two, remember what happens when you have J squared. J squared is the square root of -1 squared. So it's just -1. There's no more complex number there. So those two end up here. So now what I've done is I've broken up my S into the real power and the reactive power. And you will note there is not a complex number to be found. The thetas are all real numbers. The G's, the B's are all real numbers. And the V's are all real numbers. And because I might have 50 buses connected to that one bus, I have to do a summation junction. So my power injected at bus I is equal to the voltage at bus I, because that's consistent amongst all the calculations. And then I just increment K1 to however many buses you have. As long as there's a connection between bus 1 and let's say bus 3, then you're going to have a parameter there. If there's no connection between bus 1 and 4, then G and B are both equal to 0, right? There's no direct connection. So there is no current injection there. So that is why we use a summation. It works really, really well. We do that for P and Q. And this here is the real power injection and the reactive power injection. Okay. To make sure that our results are correct, that should equal the generated power and the demanded power. Remember, the power injected is the power going and coming and going from a particular bus. So because of KCL, all power should be accounted for, except if power is coming in externally from the bus or to the bus, from a generator or being pulled because of a load. So that's why we have to add those two onto the end. So our power injected has to be equal to the generated power minus the demanded power, both real and reactive. So these are almost the two equations that we need to solve for. They're almost the two. They're not quite there, because if you remember with Newton-Raphson, we were always doing root finding. You remember in lab, we were looking for the value of x so that f of x equals 0. So you're solving for a root. So all you need to do is subtract these two from both sides, and then you set the equations equal to 0. And those are your power balance equations. All right, questions? Because we'll look at those questions in more detail. But essentially, again, we have no way of accurately getting all the voltage magnitudes and angles. And since this is a nonlinear solution, we have to use an iterative approach. Okay, we have to just keep iterating down until we get our final answer. But before we can do that, we have a little bit of work to do. Remember how I said we have to do two things? We have to write the f of x equations. We just did that with our power balance equations. We also have to determine the voltage of the variables we're looking for. We're not looking for every single variable, every voltage, magnitude, and angle. So there's one bus that we have to have. It's called the slack bus. The slack bus is if you have a bunch of generation and a bunch of load on the system, and you've got power flow through your system, it would be impossible to accurately predict what all the generation needs to be, because you have line losses through your system. Sometimes the line losses are really high, sometimes they're really low. It just depends on the flow of power through the system. So you have a slack bus to do exactly what it says. It picks up the slack. I don't know what all the power is, so I have this one bus that is one or more buses actually, that is able to deliver as much real and reactive power or absorb as much real and reactive power as necessary to make sure that I can pick up all the losses that I can't account for. So with that being said, I have no way of knowing what the P and the Q has to be injected at the slack bus, right? Because that bus can either absorb or supply any amount of real and reactive power. So I can't write power balance equations for the slack bus, can I? Because I don't know what PG and PD or QG and QD are for those buses. That's a problem, isn't it? Because I need equations to solve to be able to check my answers are correct. Well, the way that we get around it is we're going to specify not only the voltage magnitude, but also the angle. That's going to be our reference. We're going to set our voltage at this bus that is going to be controlled to whatever magnitude and angle of voltage that you need, and then it'll supply or absorb as much P and Q as necessary to maintain that voltage. That's the slack bus. So when we think about writing equations for the slack bus, how many equations can you write? None. Can't write any equations because you don't know what the power injected is supposed to be at the slack bus. But that's okay, because however many unknown variables, there are near 0. We've specified the voltage magnitude and angle, so why do we need to write any equations? We don't know we don't need to know what those are, because we know what the voltages are. We've already specified them. So a slack bus, no equations and no unknowns. You know the magnitude and the angle. So you don't actually have to do any calculations at the slack bus other than the power exiting or entering the slack bus. Next, well, we have a bunch of load, right? Remember, the customer is paying for our bills. And so we darn well do what we need to do to make sure the customer gets the power that they expect. So we specify another type of bus called a load bus, that we will tell it what P and what Q is needed at that bus. Okay? Now, a load bus does not necessarily mean it has to be load. It could be generation. The idea of a load bus, and a better term for it is a PQ bus, Because a PQ bus means you know the P and the Q that are scheduled at each of the buses. So that's a good thing because for a PQ or a load bus, the equations that we can write are P and Q, right? We can write P and Q equation because we know the scheduled power. We have enough ability to go ahead and figure out what the power injected is there, which is great because of the unknowns. We have no idea the magnitude of the voltage and no idea of the angle associated with the load bus. So we can specify P and Q. We can't specify V and theta. You can't control them both. The last bus is a generator or PV bus. So typically a generator bus in the real world, what you do is you try to set the generator to operate at a certain power, 500 megawatts, let's say. And then you have a separate controller that monitors the voltage, and it's trying to fix the voltage at a certain level. So the equations that you can write, that you can solve for, I only can write an equation for P, right? I can't write an equation for Q because I don't know what it is. I'm setting the voltage to be fixed, and that generator is going to go ahead and monkey around with whatever reactive power it needs to inject or absorb to make sure that that voltage is fixed. So equations I can write is P. My unknown here is theta. Okay. So maybe I'll even have a known over here. So known is nothing. And the known here is voltage. I know the magnitude of the voltage. Again, that works out perfectly because for every time I have an unknown, I have to be able to write one equation to check if my results are correct. So by having a PV bus, I specify the power that is injected at the bus, which means I can write a power balance equation there. But that's a good thing because I'm allowed to calculate the angle theta. I don't need to calculate the voltage. So this is super, super, super important when you're actually going ahead and setting up your system. One of the very first things you need to do is specify the bus types for each of the buses in your system so that you can actually figure out what equations do I write and what unknowns do I need to solve for. If you don't do that, you're stuck because you'll just end up writing a bunch of equations and most of them will be useless because you can't do anything. So that's kind of a big step, is identifying a slack bus, a generator bus, or a load bus. So let's think of some examples here. What if I have a bus here and it's connected to a generator, and the generator is putting out 100 megawatts and it's controlling the voltage. Whoops. It's controlling the voltage so that the voltage is, we'll call it 1.0 per unit voltage. What type of a bus what type of a bus would you call it? Load, slack, or generator bus? Got three choices. Load, slack, or gen. Generator bus, right? How about over here? I've got a customer and they're pulling 500 megawatts and 300 megabars. Type of bus is that? Load. How about I go ahead? Now I put a capacitor bank over here. Yes, sir.
For the first one, for the generator bus, you said that you give 100 megawatt.
The generator is designed or is operating at the fact that it's putting out 100 megawatts at 1 per unit voltage.
Or 1 per unit voltage.
Yes. Yep. So I put a capacitor here, and let's say it's a 10 megavar capacitor. What kind of a bus is that? Load, gen, or slack? Slack?
load.
Load? Why is it a load?
But we have PV.
Wait a minute. But B just said, this is a load bus because we have P and Q specified. Do we? I only see 10 megavar. So is everybody saying B is wrong? Everybody's afraid to say yes. I'm not saying he's wrong. He's actually right. How much power does a capacitor consume? Not a hard question. 0. So don't you know P and Q at a capacitor bank bus? Just because I didn't say P equals 0, we're all pretty smart. We've all had circuits before. We know an ideal capacitor consumes no real power. So what am I trying to tell you? Remember when I said gen, slack, and load? It's better to call it PV, PQ, and there isn't really a good one for slack, so we call it V at an angle of theta. So when you're looking at your bus types, do you know P and V? Do you know P and Q? Do you know V at an angle of theta? Okay, those are the key things. Because over here, I have to solve for theta. Over here, I have to solve for V at an angle of theta. Over here, I've got nothing to solve for because I specified V at an angle of theta. Okay, so again, going through this process and looking, what are the knowns and what are the unknowns? More importantly, can you write your power balance equations, your P and Q equations? You can't write them if you don't know what they're supposed to equal. I know P and Q here, so I can write P and Q. And you should never have a load bus, a generator bus, that also specifies V at an angle of theta. And the reason why is because you've scheduled 500 megawatts and 300 megabars, but the power is coming in from the rest of the system. So that power to deliver that, the voltages has to be adjusted up and down based on how the rest of the system is operating. So I can't just willy-nilly say, well, this is going to be 500 megawatts and 300 megabars at an angle at 1.0 at an angle of 15. You can't do that because there's no way you could design the system so precisely to get that. Yes, sir.
What which type of bus did you go for? Like if it's not something, which bus did you go for? Like what is characteristic of determining it?
What is
how do you pick it?
So all I do to determine which bus type I'm going to use is here. Do I know PV, PQ, and V at an angle of theta? If I know those, that's where I specify.
Let's say you are the designer and then.
Ah, great question. So if you're designing a system, how do you pick the bus? Well, there's a couple ways to look at it. First off, you have to have a reference bus to make sure to pick up the slack. So you have to have a 1 at an angle of 0 bus because you can't perfectly predict the system. Usually a 1 at an angle of 0 is a really large nuclear plant, something like that, that can pick up all the slack in the world and doesn't have any problems. So that's usually set based on you're the big boss and you kind of dictate what the whole system is. The other type of buses are based on what's connecting. If I'm a generator, I'm most likely going to be operating that in PV mode because I want to sell megawatts only. So I definitely want to lock in the power output because that's how much money I can make. And the voltage has to be within reason so I don't damage my equipment. So if I'm a generator, I'm normally connected to a generator bus. The load bus is you're serving customers. So most buses will be load buses. But again, if you have a cap bank, that becomes a load bus too. It's just a 0 megawatt load. And there may be cases too when you have to operate your generator not in PV mode, but in PQ mode. And the times that you do that is because your voltage in your system is so bad, you don't want to burn up the winding on your generator. So you actually set it at a fixed Q value, and then it outputs whatever Q you've told it to output within reason. But most of the time, that's how it's set up. Most of the time. So this is the case, right? If you blow up your generator and you push it too hard, you can't be a PV bus. You actually have to move to a PQ bus. And now, especially for renewable energy projects, they're moving a lot of them to fixed power factor So you put a certain output power and a specific power factor. So you're changing a lot of the generator buses to load buses, which again is perfectly fine. It just means you have to write a couple of equations. So again, if you push the generator too hard to maintain voltage, you lock Q at its limit, and then you run the system, you run it as a PQ bus. All right, so let's move on to our other slide. So we should have started at this point, but the internet folks did not support us that day. All right, so here are our equations again. Whatever switches over. Okay, so here are our real power and reactive power equations broken up so that you don't have any complex numbers. So we just developed those. We've already specified slack, gen, or load bus, so we can come up with power balance equations, and we can also come up with the unknown variables that we need to solve for. Now, we're going to make an initial guess of our voltages. And you remember in lab, we checked, did our initial guess work out? So we checked all of our power balance equations, and do they result in 0? If they do, then we guessed correctly. If not, we're going to have to go back in and readjust and go ahead and update. So here are our equations. This is the power balance equation. So we're setting these equal to 0 here, right? Again, we're doing root solving for our equations. Now, if you remember during lab and even during class, I was very specific about doing rows and columns. If you remember, I said, make sure you do F1, your rows, F2, F3, F4. You do those as rows, and then your columns are your variables. Hopefully, you'll see why that's really important here, because these are going to be all my power balance equations. And then I have all my delta Qs. And my variables, I'm going to put my thetas first, and then I'm going to put my voltages. So now, when I'm going to build my Jacobian, these are all going to be power balance 1, power balance 2, power balance 3, and on, and then reactive power balance 1, reactive power balance 2, and on and on and on. This variable, theta 1, theta 2, and on and on and on. And then this is V1, V2, and on and on and on. And the reason being is because these matrices can be partitioned. So these are all set up to look at sensitivities to, like in the case of delta P1 and theta 1, how sensitive is power flow at real power flow at bus 1 because of a change in angle in the theta 1. And so the idea is you can get a lot of information just by looking at this sensitivity analysis. And that's actually more of a graduate level topic, but you can actually predict how the system's going to respond just by looking at these parameters. So your Jacobian is all based on the approaches that we've been talking about. Rows and columns, make sure you have it set up. Now, this is totally up to you. Totally up to you. But I've got it set up here that I actually am showing you how to write the Jacobians. So you can see that this Fi of x, that's the real power balance equation. So this shows you how to calculate the partial of the real power balance equations with respect to theta 1. So it's important. At bus I and the angle theta I, you use the equation that's shown there. If you're at bus I, but you're trying to calculate the angle J, it's a simpler equation. And it's kind of highlighted here that J does not equal 1. This, you can go ahead and you can just write these equations, sort of mathematically. And that's what all these load flow programs do. They basically have equations where they have while loops, and they just spit out all these different equations. Hopefully you have a little more intelligence. You can do it on your own and do it that way. So here's the power balance equation for I with respect to theta I. theta J, and then we do the same thing for VI and VJ. So every one of these equations you have to write at a generator bus and at a load bus. You have to write the power balance, the real power balance, and then you got to do the 4 components of your Jacobian, if it's a load bus. Do the same thing for Q. And again, you don't have to use this format here. You can just take partial derivatives if you want. That works perfectly fine. But the idea is that you're going to end up with a set of equations that look pretty similar to this. So I'll leave it to you. I actually just do the partial derivatives. I find it a little bit easier. And so that's what I end up doing. But those are your generically written P and Q equations. And then when you're all said and done, here's what your Jacobian looks like. It is a lot. Your Jacobian could have 1,000,000 by 1,000,000 entries. So you can see why it takes days to do a load flow, because inverting a matrix that's 1,000,000 by 1,000,000 is a lot of processing power. But I partitioned it. You can see I've got all the P's in the, all the P's lined up in row, P1 through the end of the line. And then I did Q1 through the end of the line. And then my columns are the thetas, 1 through N, and then V1 through N. Here's the important thing. Be careful not to swap theta 1 and theta 2. You want to do everything in order, because if you start swapping where things go, your results are going to get really heinous. And for those of you who are with me lab, one person had their results not converging because they didn't have a minus sign in their Jacobian. So one sign change will completely screw up your result. So it's very important to make sure everything goes in the right position. Here is the Jacobian. Go to partition. Again, looking at sensitivity analysis. And then we just update. So instead of calling it theta, I called it delta. Sometimes that's called the torque angle or the power angle, but it's the same thing. And you can see how you're going to update each and every time using our Newton-Raphson approach. Okay? Once you're done, once your power balance equations all equal 0, then you've got your final bus voltages. Now you can calculate power injected at each bus. That is unknown, like a slack bus. You don't know what the P and the Q are. You can actually calculate what the P and the Q need to be at those buses. All right, do an example. So this is a pretty simple example. It's only 2 buses, but you're going to see how quickly things get out of hand or out of control just by working with a 2-bus system. So we have 2 buses. We have a transmission line interconnecting the buses. And you can see that it's 0.1 J. And we'll assume that that's in per unit because they're not told otherwise. And we've got to basically start from scratch and build the whole thing. So step number 1, let's solve for a Y bus. Remember, this impedance here needs to be converted, right, to an admittance. And then to build our Y bus, the sum of the admittances all connected to bus 1, there's only one of them, minus the admittances between bus 1 and 2, and that's it. You only have 2 buses, so you're done. And then you take because you take the transpose of the matrix, so the rows become columns. And then the same thing, take the sum of the admittances connected to bus 2. So this is a pretty easy Y bus, right? It's only got one element to worry about. So that would be step 1 of what you would need to do normally. Now, our step 2, solve for your f of x equations, or not solve for them, figure out what your f of x equations are, your power balance equations, and then figure out what variables you need to solve for. So looking at this system, the 2 buses, can you tell if bus 1 is a slack, load, or gen bus? And why? Why is it a slack?
Oh, no, it's not.
It's not a slack.
Not a plan, it's not. I think it's a gen. No, wait. Load, because it's
Load.
MV and MVR.
He went through all 3, right? One of them has got to be right.
I think it's load, because it's B and Q.
Who thinks it's a load? Bus 1. I said bus 1, right? Okay, who thinks it's a slack? Who think it's a gen? More than half the class. Who thinks it's a load? Couple people? I'll raise my hand for a slack bus. Why is it a slack bus? Don't I know the magnitude and the angle of the voltage? One at an angle of 0. I don't know P and Q at the bus. Did I tell you how many megawatts and megavars are there? So how could it be a load bus? I don't know what the load is. How can it be a generator bus? I don't know what the P is. But I do know the magnitude and the angle, which means this is a slack bus. How about bus 2?
Good.
Sure? Anybody think it's a slack bus?
Think of-
How about a gen bus?
oh. There's S,
S on bus 2? I don't see an S.
no, Q and P.
I see P and Q. That means it's a PQ bus, which means it's a load bus. So this is a load bus, which means I have to solve for V and theta, and I can write delta P and a delta Q. All right, so I have to solve or write equations for delta P2 and delta Q2. And my unknown variable matrix, right here, theta 2 and the magnitude of V2. Everybody see that? That's why it's so important to make sure you understand how or what is a slack bus, what is a load bus, what is a gen bus. Look for P and Q. Look for V. If you have P and Q, it's a load bus. If you have V, it's a slack bus. If you have V and P, it's a gen bus. That's all you're looking for. And again, the capacitor bank is a perfect example. I looked for P and Q because I know a capacitor consumes 0 watts. So I knew P, right? I didn't have to specify it. I knew what it was. All right, so let's go ahead and start writing our equations. So I'm writing delta P2. So this is delta P2. So I know that I is going to equal 2, right? And N is going to be equal to 2. So it's a total of 2 buses. So I know that this right here can become a V2. That's fixed, right? K is the one that varies, not I. So I can actually move this right out front of the equation. So now I start out with K equal 1. So I have V1. All right, now I got to go and get G and B from my Y matrix. What are G and B out of Y bus? Give me G first. G, I, K, which in this case, 1, 1. What is Y, 1, 1? What is G, 1, 1? You ready? What is G11?
0.
0, yeah. Do you have any real part in your line impedance? It's purely imaginary. So how can I have a G term if it's purely imaginary? So if you're confused, you can say your Y, whoops, sorry about that. You can say your Y bus is 0 minus J10. G11 is 0. Which is great because there are no G terms in the Y bus. So goodbye, goodbye. Because 0 times the cosine of theta ik or the sine of theta ik is the same, right? So now I've simplified it quite a bit. Let me go ahead and I'll copy this over and put it on whiteboard. Come on, move up. All right, so now I'm going to go ahead and write my power balance equation. And I'm going to do the full Monty here. So delta P2 is equal to the magnitude of V2. Now I'm going to go in my summation. So I have V1, no GIK, so that's gone. This is B11 sine theta 11, right? So that was K equal to 1. Now I go K equal to 2 plus, because it's a summation, V2. And I might get sloppy in news. I apologize for getting magnitude. That's V2. B12, right? Because it's IK. So it's 1, 2. Sine theta 1, 2. Now I'm going to subtract PG1 minus P, not 1, 2, right? Okay. And that is my power balance equation. When I get the correct result, I get 0. Okay. That's my first power balance equation. Now let's go and do my reactive power balance equation. So I'm going to drag this. Plop it over here. And now I'm going to do delta Q2, right? I'm not doing delta Q1 because I can't. I don't know what QG1 and QD1 are, so I'm lost. I'm not even going to bother writing those. Same deal. I move out my V2 out front. Then I do my summer. V1 magnitude, no GIK. Got to be careful because I have a negative B12 there, right? So make sure I factor out the B12. Then I take the cosine of theta, it's 2, 1. I'm being sloppy here. This is 2, 1, 2, 1. Let me clean that up. And this should be 1, 2, right? Theta IK is 2, 1. That should be 2, 1. Sorry about that. Theta 2, sine of theta 2, 1. Oh, wait a minute. That can't be. Oh, yeah, that's correct. These should be all the same now. Wait a minute. Hold on. This is V1 times BIK. So this is B22 sine of theta 2, 2. Sorry about that. It's B21 sine theta 2, 1, and then B22 sine theta 2, 2, because I incremented K. So I is always equal to 2, and K goes from 1 to 2. So it should be 2, 2 for the last two. So this is a cosine of theta 2, 1. Then I add to that the magnitude V2 times negative B22 times the cosine of theta 2, 2 minus QG2 minus Q demanded 2, and that equals 0. Those are my two fully written out power balance equations. Yes, sir.
It's QG2 minus QE2
QD2
or D2,
demanded.
the G2 minus QD2.
D as in David. Okay, so these are valid equations. But if I can simplify them a little bit, it might make my life easier. So let's see if I can simplify. That is the magnitude of V2. That's an unknown. No simplification there. Do I know anything about V1 magnitude? Yeah, it's given. V1 is 1 at an angle of 0. So the magnitude of V1 is 1. That's not a variable. It's a known number. I just call it 1. B21, I've got to dig that out of my Y bus. So B21 is it 10 or J10?
And
Not J10, it's 10, right? Because we factored out the complex numbers. We can't have any complex numbers there. Now this becomes the sine of theta 2 minus theta 1, correct? Yes, sir.
But B minus J10, I think minus.
B21 is?
Minus J10.
It's positive J10. It's 2 comma 1. Right? That's positive J10. No?
B is equal to, well, that's the one.
Yeah, this is the admins, but remember to build the Y bus? To solve for the self admins, we sum all the adminses together. To get the off diagonals, we have to take the negative of the admins, right? So the negative J10 becomes a positive J10 because we took the negative of it. Okay? All right, so plus V2, which is unknown, and then B22, that is negative 10, times sine of theta 2 minus theta 2. Subtract from it PG2, which is 200 megawatts or 2 per unit power. Actually, that's output power. So there's no generated power minus 2 per unit real power. That equals 0. Let's do the same thing for the next equation. V2 times, already determined that V1 is equal to 1. Nothing to do there. This becomes negative 10. This is the cosine of theta 2 minus theta 1 plus magnitude of V2 times a positive 10 times the cosine of theta 2 minus theta 2 minus no generated power. No generated power, but the demanded power is 1 per unit, and that equals 0. Are these simplified down? Are you happy that these are simplified down enough? I'm not. Didn't we say that V1 was 1 at an angle of 0? So doesn't theta 1 go to 0? Right? Theta 2 minus theta 1, and theta 1 is equal to 0, is just theta 2. So this first expression here becomes 10 sine of theta 2, right? Over here, what happens to V10 times minus 2 times the sine of theta 2 minus theta 2? What is the sine of 3 minus 3 equal to? Get it right. That's always 0. That never exists because the sine of theta 2 minus theta 2 is always, always, always 0. So this is completely gone. This whole thing doesn't show up in your final answer. The thing that does show up is not 4, 2. The final balance. That's it. That is your simplified power balance equation.
Where did the come from?
What 2?
Is
Right
that
here?
minus 2? Yeah.
Yeah, that's the demanded power. So if you go back to the one line, I'm demanding 200 megawatts or 2 per unit power. Everybody understand how to do that? Because it behooves you to simplify your equations down. Because guess what we're going to do next? Partial derivatives. And if you've got a lot of V's and thetas in there, you're going to be doing partial derivatives for a long time. But taking the partial derivative of this doesn't look all that ornery, does it? Let's do this one. Magnitude of V2. 1 times negative 10 is negative 10. And that just becomes the cosine of theta 2, right? Because theta 1 is equal to 0. So that doesn't subtract. What about over here? What's the cosine of theta 2 minus theta 2 equal to? Oh, it's just 1, right? So that one doesn't go away. It just becomes V2. And that is our second power balance equation. So we have two power balance equations that are not that complicated. Our final one for delta P2, just kind of writing it here, cleaning it up. 10 V2 sine theta 2 plus 2 delta Q2. Let's see, I have negative 10 V2 cosine theta 2 plus 10 V2 magnitude squared plus 1. Those are our two power balance equations. Now I've got to do the Jacobian. So remember, this is my delta P2, delta Q2, theta 2, and V2. So I need the partial of delta P2 with respect to theta 2. Anybody need any help understanding how to do that? Everything is constant except for theta 2. So I end up with 10 V2 cosine of theta 2. That's that first power balance equation. My second power balance equation, delta P2, with respect to V2, is 10 sine theta 2. My third power balance equation, delta Q2, with respect to theta 2. So the derivative of cosine is negative, right? Negative cosine, or negative sine, sorry. So that should be 10 V2 sine theta 2. And the last partial derivative I need, negative 10 cosine of theta 2 plus 20 V2 magnitude, right? Because that's V2 magnitude squared. Yes, sir.
Before you can't find delta P2 and Q2, you don't put delta 1 or V1 or delta P1 or delta P.
I did have them. They're in here, aren't they? I see V1 right here and theta 1 right here. But V1 is 1 and theta 1 is 0, and it never changes. So I'm certainly able to keep them as variables, but why bother? I'm not doing anything. I'm not adjusting them. So if you can spend a little time, looking through it with them intelligence and saying, hey, this is 0 and this is 1, they just drop out. And then it makes your partials much, much easier to do. So now I have my f of x equations. I have my Jacobian. Now just write it. So here are my two power balance equations. You can check to see if those are consistent. I believe they are. Here's my Jacobian, if I did it correctly. Now rinse and repeat. Do the iterations. And then once you're done, you can solve the values. I'm not expecting you to do that by hand. I did it with, anybody want to guess? That's how you write the code in MATLAB. And I was not super fancy because you can see I already substituted V1. I took V1 out of these equations. I could have kept them in there, but the V1 goes away. So I wanted to match what we had on the slides. And instead of calling it theta 2, Theta, I just put T just to make it a little bit easier to follow. And then I just set up my iteration matrix, right? While the absolute value of delta x, remember I said you want f of x to be equal to 0, but I also said if delta x is not changing all that much, you can go ahead in there. I still have my iteration counter. N is going to be less than or equal to 10. So I write my dp2 equation and dq2. Notice I didn't even check to see if those were going to be bad guesses, because they almost always are. So I just assume I'm going to run through and check it out. Here's my Jacobian with the numbers. I calculate delta x, negative j raised to the negative 1 times my f of x equations. I update my theta 2 and my v2, not theta 1 and v1 because those aren't changing. Increment and then rinse and repeat until I'm all done. And at that point, I'm going to check and see what does the power at the slack bus need to be. The real power of the slack bus has to be all the power delivered to the load and then any power consumed in the line. Same thing with the reactive power. I also, just for giggles, check to see does the power injected at P2 and bus 2 for both real and reactive, does it match 200 megawatts and 100 megabars? So Clear CLC. Remember, why did I put that in there? Nothing up my sleeves, right? No tricks in MATLAB, nothing fancy. This clears out everything. Gonna run it. Go over to MATLAB. And after 5 iterations, I can see that I'm going to make it a little bit bigger because, whoops, why is it going up? So the magnitude of the bus voltage is 0.855, and the angle is negative 0.236 radians, not degrees, but radians, okay? Because remember, you have to do your Newton-Raphson algorithm in radians and not degrees. And then I just check to see, all right, do I get good results? So let's go down to P2 and Q2. Hey, looks okay, right? The power injected at P2 and Q2 is -2 and -1, which means that that power is going into the bus and it's going sent to the load. So my injected power matches my scheduled power, right? It's the power that's being delivered to the load. Let's take a look at P1. Oh, P1 matches the output, but Q1 doesn't. Why isn't that 100 megabar or the equivalent of 100 megabar? Did I make a mistake?
No, the line goes through.
Yeah, the line eats VARs. It eats 68.3 megabars because it's a J.2 ohm equivalent or J.1 per unit equivalent inductor. So just to double check, my magnitudes are the same. Let's check if that angle T2 is correct. So I'm going to take T2 and multiply it by 180 over pi, negative 13.52, negative 13.52. Close enough. And you can do that in 5 iterations. That's all it takes. And the precision I got was not crazy, right? I got it into 100th of a percent. You can get more accurate, but it just takes a longer time to process. But you really aren't going to see any much more precision than what you have here. Okay, so the Newton-Raphson algorithm is all basically in the while loop here with a little bit of setup in order to make it go. The stuff over here is just to check and display my work. Because again, the whole purpose of a load flow is to figure out, are lines overloaded? Is it too much power flow from line 1 to line 2? If there is, then you got to fix it, right? You got to make some adjustments. But the only thing that it does, the whole thing, up until I get to here, and let me set a breakpoint here. So if I run it to here, look what the load flow does. It just tells me all the magnitudes and angles of the bus voltages. I know V1 and T1. I didn't know V2 and T2, so now I have them. Okay? So those are the only ones that I need to get. I didn't calculate P. I didn't calculate the P flowing from bus 1 to bus 2. I need those voltages first, and then I can calculate it. Then I can figure it out. So even though we call a load flow, right? It's checking the flow load. It really doesn't check the purpose of it is really to calculate bus voltages. But once you have the bus voltages, then you can calculate all the power flows in the system. So getting the voltages is the big part of it. But then what do you do with those voltages? Then you calculate them. Now, this would be a bad system operation because look at how low the voltage is. It's 8.554. So the system operator would have to go back and change things. And so this is where the code that I wrote isn't great because I've taken out all the V1s here. So if I wanted to say, all right, let's run it a little hotter. Let's run it at 1.05 for the slack bus voltage. It might be like, I can't do it with this one. I'd have to go back and modify it and add in the V1, which is not a big deal. but I wanted to show you the simplest one so you can see the syntax of how it lays out. Okay,
So you would adjust the one angle theta, so a higher.
yeah, so if the voltage at the receiving end, and let's go back over here. So we'll call this the receiving end of the line, that's trash. 85% voltage is customers are calling, complaining. You're probably gonna get a fine. If you're the independent system operator, you might not get a fine, but you get a stern talking to from people. They'll have to report it. All the utilities are seeing that the voltages are bad. They're gonna call up ISO New England or New York ISO or whatever transmission operator territory you're in. They're gonna complain, and you're gonna get you're gonna have a lot of explaining to do essentially. So one of the things you do is like, hey, let's goose up the voltage. Instead of 1.05, 1.00, let's see if we can go to 1.05. Does that improve things? This is such a simple system. Probably the easiest thing to do would be to like, you know what? I'm going to reduce the reactive power demand. So instead of 100 megavar, if I can drop that to 25 megavar by putting cat banks on that end, I can get much better voltages. So that's what the system operators do. It's like playing a video game without a lot of graphics. You just try something else and see if the results are better, and then they dispatch based on getting acceptable results. That's what the system planners do, the short-term system planners. Long-term, they're doing this as well, but they're not figuring out operating voltages. They're just making sure everything is within tolerance. And there's a tremendous amount of work to make sure that the system is designed and constructed. I worked on a project that was proposed 2 years ago, and if it gets approved, it won't start operating until 2032. It took 2 years of them assessing it just to even see if it was viable. And then the step that I was involved with is what kind of modifications to this existing system need to be made. And oh, by the way, how much is it going to cost? $100 million is the project I looked at. Chump change, right? That's in Long Island. So that's just for this one tiny little modification to a substation. They want to put in some 345 kV lines and upgrade substation. It's probably going to be like a $5 billion project when all is said and done. But it's New York money, so that's not Maine money. It's a different world. But yeah, that's how you do a load flow with a very simple 2-bus. You will be expected to do at least a 3-bus system. So you may have to write how many equations? 4 equations, did you say? Because you could have 2 load buses, right? You'd have to have 2 equations. How many variables would you have to solve for? That should be easy. If you have 4 equations, you have 4 variables, right? Doesn't make sense to have 3 variables because you over-design the system or over-specify the system. How big is your Jacobian going to be? 4 by 4, 16 partial derivatives you'll have to take.
Can you go back on slide 13?
Yes.
Yeah, you said N is equal to 2. Why?
There's 2 buses. So you go all the way from the bus, you start at whatever bus 1 is, and you go all the way to the end of the line of buses. So you make sure you capture all the power injections from every bus that's possibly connected to the one you're investigating or evaluating.
So for in this case, we clicking on bus 2, which means we have to check everything whether on bus 2.
Nope, you have to connect, you have to check everything from bus 1 up to bus 2. Right. That's why K goes from 1 to 2, but I is fixed at 2.
Because
I never changes.
you're looking at bus 2.
Correct. You're looking for delta P2. P2 and I are the same. Okay.
And then your J, which you said is equal to 0. Which J, let's say we have 3 buses, which J are we looking for? Are we looking at?
J?
Like G, J?
Oh, no, it doesn't matter 3 buses. What makes the G term 0 is here, right? Z is equal to R plus JX. If I invert that, I have 1 over R plus 1 over JX, which is equal to G plus, or actually minus, JB. So because there's no real term, the G term is 0.
Now, if we have 3 buses, we have 2 lines.
No, you could have more than 2 lines, you could have 3 lines, because if I put another bus down here, I could run here and here, right? I could have 3 lines.
Which one we have 3G, right?
You could have 3 Gs, yeah.
Which one are we looking at? Which one should be Z? Which one are we looking at checking?
So the G, so keep in mind, the G is only determined by the real part of the impedance between the 2 buses or of the transmission line. That's not the G, but the Y bus that you have to build, your Y bus would have to be a 3x3, right? You'd have an element here, here, here. So you'd have to build Y bus the whole way through. Okay. Oop. We can also do it with a goofy evaluation. Remember how we said nonlinear, you can always have more than one solution? Let's plug in 0.25 for the voltage. And you get a valid solution, at least in terms of Newton Raphson. But how valid is that solution? Well, let's see. Your voltage at bus 2 is 0.261. Do you think the customers are going to be happy that their voltage is 26% of nominal? What about you, the utility? Your slack bus has to put out 832 megabar. Your line is consuming over 700 megabar. That's why you get bad voltage. You started out really low. But it is a valid solution, at least in terms of Newton Raphson. But would you operate the system like this? Not if you want to keep your job for long. Okay. In the next class, we'll add some slack bus, load bus, and gen bus and look at that. But really quickly, I wanted to show you for the homework. I think I posted it, but get so many classes this semester. Let's see. I make it a little fun for you. Look at your Y bus. G is not 0, is it?
Mhm.
So you remember those GIKs that go away? Not anymore. It's a 3x3, and you'll notice that over here, you see that it specifies V3 as 1.04. So even though I show power here, I'm still specifying the magnitude of the voltage. So you have to be smart enough to recognize that, sorry, that doesn't mean anything to me because it's a PV bus. I can't have a P, Q, and V bus. So that is not a relevant term. Same thing over here. Nope. That's my slack bus. I got magnitude and angle voltage. So I don't care what the 2 plus J1 is. Okay, I can't write those equations. I can add those in after the fact, that goes to the load, but that's not the scheduled or demanded power. I still have to be able to calculate it. So you're going to have, this is going to have 3 equations. Your Jacobian is going to be 9 by 9, and your G terms don't go away.
Now it seems as if you prioritize the slack bus first, because you could have been like, fine, this is the load bus. If that voltage goes away.
Well, you're sort of right. I prioritize a slack bus because every system to be able to do a load flow has to have a slack bus. You have to have at least one slack bus because you got to make up for the differences in the line losses. If you don't have a slack bus, then you can never get power balance because you can never accurately predict what the line losses are going to be. It's too difficult. So you always have to have one slack bus to pick up the slack. It also provides a reference too. It's 1.04 at an angle of 0. That's my reference. So you've got to have a slack bus. How many load buses and generator buses you have after that? It's irrelevant, but you need at least one slack bus. You can have 10. You can have 50. You wouldn't want a real world system that has all slack buses because then, you know, it would not be operable, but you can have multiple slack buses if you want. Okay. I even gave you a practice problem if you want with answers. But you notice there's only 2 problems here because it's going to take a long time. That number 2 is probably going to take you a few hours to do. Just one problem.
But in MATLAB,
Well, MATLAB will do the calculations very quickly. Will you code MATLAB correctly to get the results very quickly? Probably not. It takes a long time. So that's why I did at the beginning of class. I just said, you know what? I'm going to do it all on paper. MATLAB is just my calculator. So I did it all on paper and I simplified those equations down. If you can simplify and do it correctly, you make your life a lot easier. But at first, you don't want to simplify it. You want to see all those variables and make sure as they drop out, okay, that goes away. What's going on with this one? What's happening with that one? And the terms start to drop out, and then your equations get a little bit easier to manage. But when you start, you've got to work. Okay, any questions on this? No questions? I will say that, again, this is probably the toughest material in terms of doing it because there's just a lot of, it's not a hard algorithm to implement, but it does take a lot of meticulousness to get it right. So make sure when you're trying to do these, you've got plenty of scrap paper and you're very clear in how you do things, because otherwise you're going to end up with some pretty wonky results. And like I said in lab yesterday, one student had a minus instead of a plus, or plus instead of a minus, and their results were wacky. And it's a needle in a haystack, right? Looking for a minus sign. Sometimes it just takes forever to find those. Questions? All right, well, if there's no questions, I will end class. I'll make sure that the homework is assigned. I'm thinking the homework assignment will be due next either Tuesday or Thursday, because our next exam is coming right up, right? I think it's a week from Monday. All right. So I'd like to have it due at the beginning of class. So it'll probably be due a week from today, because that'll give us a chance on Thursday to answer any questions, because Monday we have the test, right?
If Monday?
Not this Monday, the following one.
Oh, okay.
All right, y'all. Have a great day, and I will talk to you soon. Take care, everyone.